Okay, hey everyone. I got to thinking that Calc 2 could use one more lecture on something called Fourier Series. Okay, it's really a cool topic, and it's something which can you can take uh, days and weeks to learn about all the things there is to know about it. It's very applied, but let's just have an introduction to it and see once what there is to it. It's kind of cool. So here's the idea. We just finished talking about taking a function f and writing that function as a polynomial, as an infinite series of powers of x, if you expand around 0. So you have a naught plus a1x plus a2x squared and so on. That goes on forever. And that thing, if we want it to converge to x, then we have to find what are those values of a, what are those constants equal to. And it turns out that a sub n is equal to the nth derivative of the function at 0 divided by n factorial. And then you add all those things up. Those are all your constants. You multiply those by the values of x to the n, and you get yourself quite often an infinite series that converges to the function. And the idea is this, that we get these two functions, we get this polynomial to match up with the function at one particular point. So not only does the value of the function, but also the first derivative and the second derivative and the third derivative all the way out, the nth derivative, all those derivatives all match up with the function at some particular point. And then by having everything match up at one point, then the hope is that when you travel out from that point, the behaviors will stay the same. And in fact, they usually do. They often do. Okay, so that's the idea of a Taylor series. Okay, that's a Taylor series. But now we're going to use another idea to get something that converges to a function. If you think about it, lots of things in the natural world are periodic in nature. If you look at your heartbeat, it, ba-boom, ba-boom, it goes like this, and like this, and like this again, okay? Or any sort of a biological rhythm. Or if you look at the temperatures over the course of a year and do that year after year after year, or you look at what happens day to night with the temperatures going up and down, or you have a swinging door, or you have waves lapping at the beach. There's all sorts of things that just oscillate back and forth and back and forth. They're kind of natural oscillators. If you go down a stream, you'll sometimes see little twigs in the stream just going like this, perpendicular to the current. It's really kind of an interesting phenomena how that works. But anyway, the point is, since nature works that way, we want mathematics to be able to describe those kinds of things. And that's why periodic functions are so important. In particular, the trig functions, the sine and the cosine in particular, right? They just keep doing the same thing over and over again. And since they do, they're good for modeling things in the natural world that do the same thing over and over again, okay? So that's what the trig functions do. So with that in mind, here's what we want to do. We want to ask, is there some sort of a way to get a bunch of these trig functions that will converge more and more closely as you go out farther and farther, converge to some sort of a periodic function, okay? That'll make more sense as we go. But before we do any of this stuff, we need to just get some interesting facts about trig functions that are super important for all of this to work, okay? Back in Calc 1, I think I taught this, that the formula for the sine of a plus b is, and the cosine, you put those one under the other, and then you say the little jingle: sine, cosine, cosine, sine, cosine, cosine, sine, sine. I'll do it again: sine, cosine, cosine, sine, cosine, cosine, sine, sine. And then you alternate putting a's and b's, and you put a plus in the top one and a minus in the bottom one, and you got them. Of course, I haven't proved it, but those are the two identities that you can prove with a little bit of some triangles and so on the unit circle. So once you have those, then I'm not going to go into this in detail because I'm assuming at this point in your mathematical career you know most of this stuff. But the sine of a minus b, wherever you see a b, you put a minus b, and the sine is an odd function. An odd function is one where you can bring the negative outside of the function and bring it out here. An odd function means that f of minus x is equal to the negative of f of x. In other words, whatever it does over here, it does exactly the opposite over there. An even function is one where whatever it does there, it does exactly the same on the other side. This is odd, this is even. So the cosine is even, the sine is odd, and so when you put negatives in there, here's what you end up with, okay? So then, if you add 2 and 4, this is 2 and this is 4, add those together, these things will cancel out, and you're going to end up with the cosine of A times the cosine of B is equal to these two things divided by 2. If you subtract 2 from 4, okay, take this one, subtract this one, then these two things go away and you get double this. So you get sine A sine B is equal to this minus this over 2. And then finally, if you add 1 and 3 together, this one and this one, then what goes away? This goes away, and we end up with 2 of these things. And so you divide by 2, and you get sine A cosine B is equal to this plus this over 2. Okay? So, why are those important? Those are important because now, if I ask, what happens if we integrate? By the way, let me remind you of what two other things are going to be super important. If you integrate an odd function, okay, it does exactly the negative over there. If you integrate an odd function from negative b to b, then the value of that is going to be 0. Agreed? Because whatever it does here, it's the exact opposite there. One is positive, one's negative, and so it's going to be 0. So if you take an odd function and integrate it from negative b to b, the same value, one positive, one negative, you're going to get 0. On the other hand, if you have an even function and you integrate it from negative b to b, then that's going to be just double what you get by going from 0 to b. Okay? So you can save a little work by doing that. Okay? So that's going to be important here. Okay? So, how does that all tie in? Well, if you ask what's the integral of this time of sine of mx times sine of nx, and that's where all these things are integers. M and n and k over here, these are all integers, and positive or negative. And if you take this right here and you integrate it, what are you going to get? Well, you take this and you can replace this thing with this thing, and then you notice you're going to just get the integral of this, and these two things, just check them out. You're going to get constants times x in there, integrate it from negative pi to pi, and since this is a periodic function, that's all going to go to 0. Okay? You can spend a whole lot of time going through all the details here. I'm giving you kind of the skeleton of it so you can fill in the details. Same thing here. If you have, look at number 6, and you look at this, the sine times the sine, you can replace this thing here with this, and when you integrate that, you're going to get 0. If you have the cosine of mx times the cosine of nx, again, go back to this one, and you can replace this with this, and you go through, and you'll see that you're going to get 0. And that's when m is different from n. Okay, that's when those are different values. On the other hand, if m is equal to n, then sine of mx times sine of mx is the sine of mx squared, and you use the same thing again, and you're going to get this is the sine times the sine. You're going to get cosine of 0. Cosine of 0 is equal to 1. There you get this. Then you get mx plus mx is 2mx. See that? So you get this thing. You integrate that. This part gives you 0. Here you have 1/2 from negative pi to pi, which gives you pi. And the same thing happens here. You take cosine squared and you use this thing right here, and you're going to end up with a cosine of 0, which is 1, and then you're going to get the cosine of 2mx right there, and that's going to give you pi again. Okay? So those are very important properties of sines and cosines. If you've had any Calc 3, then you talk about vectors, and you can talk about vectors being perpendicular. To be perpendicular geometrically means that there's this 90-degree angle between them. But even in higher spaces, basically what it means to be perpendicular, if you know this, that's great. If not, not a big deal. But it means that their dot product is 0. Their dot product is 0. And what we're and if the dot product is 0, that means they're perpendicular. That means that they're orthogonal. Another word, orthogonal. Okay. And so what we're really saying here is that if you think of these functions as being vectors, then all of these functions are orthogonal to all the other ones. If you think of the inner product as being what happens when you take the integral of these things, then basically you're taking the inner product and they're orthogonal to each other, which is why they're all 0. On the other hand, if you take any vector and multiply it by itself with the dot product, they're in the same direction, so then you get the size of the vector. And same sort of thing here. So that's why if m is equal to n, you get a pi out there. Okay, very good. So that's all part of history now on this YouTube video. So I'm going to get rid of all that to give myself some space. Okay, it took a while to write it all up there. I hope I didn't erase it too soon now that I think about it. And so now we're going to come back and we're going to say, okay, let's get rid of this as well, because now we're talking about this other kind of series called the Fourier series. So what we're going to do is we're going to say, okay, let's take our f of x the same way we did here, and we just took our f of x and we wrote it as some constant plus some constant times x and so on. We're going to do the same thing here. We're going to take a sub 0 times cosine of 0x plus a1 cosine of 1x, a2 cosine of 2x, going on forever. And then, second row, b0 times the cosine of 0x, b1 times the sine of x, b2 times the sine of 2x, and so on. First of all, right away, I can simplify some of this. The cosine of 0 is 1. The sine of 0 is 0. So that goes away. And so we end up with this being gone. Let me get rid of this. And this is just going to be a naught right there. So we can do that right off the bat. Okay? And so what we're going to do then is we want to find out what constants do we need here so that this thing here will converge to this function f of x. Okay? So we need to find those constants. And the way we do them is by integrating everything. So for example, if I were to integrate this thing right here, here's f of x, from negative pi to pi, we're assuming here that our periodic function is this is some sort of a function that does something crazy, and it does something crazy there, the same thing, and it's going to go from negative pi to pi. So it's some sort of a periodic function, whatever it does. Okay, it doesn't have to necessarily be odd or even. It could be like this, whatever it is, from negative pi to pi. That's what it does. But it just starts over again. It's periodic. So at this point, it just starts over again and does the same thing over and over and over again. So it's a periodic function. Okay? To be periodic means that f of x plus whatever your period is just gives you back f of x again. So it just starts back over again. Okay? So given that that's our function, here's what we do. We take the integral from negative pi to pi, and the same thing here. If I take the integral of this thing from negative pi to pi, look at what's going to happen. I go here, take the integral of each one of these things, And notice that all of these things, when I go from negative pi to pi, all of these things are going to end up giving me 0. Because from negative pi to pi, if you think about what the sine and the cosine are like, there's the sine, here's the cosine, it looks like this. They're going to give you 0. If you double it or triple it or whatever, it's just going to do it 3 times as fast, but it's still going to end up being symmetric there, and you're still going to get 0 all the way. Again, all these things are things you need to check, but just check them out. So all of these things will give you 0, and the only thing you'll be left with is a naught. And so a naught from negative pi to pi is going to be the integral of this thing. And so these all other ones are all 0. And so this is going to be a naught times 2 pi, right? That's going to be a naught. It's going to be equal to a naught times 2 pi. And so you divide both sides by 2 pi, and you get that a naught is equal to 1 over 2 pi times that right there. So there's your a naught right there. Okay, how do we find these other constants? Well, say we want to find constant a sub k. Let's get rid of this now. Okay, we want to find a sub k here. So here's what we do. We multiply this whole thing by the cosine of kx. So you multiply this by the cosine of kx, and you multiply everything, up here. You multiply this one by the cosine of kx, and you multiply all these things by the cosine of kx. Okay, multiply both sides by the cosine of kx. So what do you get? On this side, you're going to get f of x times the cosine of kx. On this side, you can distribute this through, and each one of these things is, I missed, this should have been a 1 right there, I guess. Oh, no, that's the original one right there. And then this thing, I guess I didn't do number 1, but I included, let's see, this is, I forgot number 1, but here's number 2, which is cosine of 2x times the cosine of kx. You have all those things. Where you finally have cosine of kx, then notice you're going to have a sub k times the cosine of kx times the cosine of kx. So you're going to get that thing squared. Then you get all these other ones where k is different from those other constants, and then you include all the signs as well. So here's all the signs where you have the sine of anything times the cosine of kx. So you have all that, and then you integrate both sides. Okay, now you integrate both sides, and here's the key. The key is that by what I erased over here, all of these things are going to give you 0. This gives you 0. All of these give you 0 when you integrate them. All those things are going to give you 0. This one's going to give you 0. They're all going to give you 0, with the one exception of this thing where these are all orthogonal, but this one you're going to end up with, I erased it, with pi. That one's going to end up with pi. Okay? So what do you end up with? Here you go, negative pi to pi. So you're going to get this thing right here is equal to, you're going to get this thing right here from negative pi to pi. So that's going to give you a sub k times bring the a sub k out, and this whole thing here, when you bring your a sub k out, it's like this, and you just have this, and this whole thing here gave you your pi, and so now you can solve it for a sub k, and you get a sub k is equal to 1 over pi times this right here. And if you do the same thing with the signs, you can get your b sub k is equal to 1 over pi times f of x from negative pi to pi of sine of kx dx. So there we have our formulas for all of those constants. Okay? And so now that you have those formulas for all the constants, we can actually use them to solve some interesting problems. Okay? So here's example 1. Okay, example 1, here's our function. Our function is just f of x is equal to x, and this is on the interval from negative pi to pi, and then it just starts over again. Okay, so it just goes like this, and then it starts over again and just does it like this and does it over again, over and over and over again. It's like called a sawtooth sometime. Okay, just diagonal lines like that. Okay, there's our function. So what's going to happen if we calculate all of these things? Well, here it is. A naught is equal to just 1 over 2 pi times the integral of x from negative pi to pi dx. That's an odd function. Odd function on a symmetric interval there is going to give you 0. So that's going to give you 0. If you take any of the other a sub k's, you're going to get 1 over pi times negative pi to pi. Here you're going to get x. Here you're going to get cosine of kx dx. Okay, let me make sure that you're still with me here. Okay, very good. Okay, and here again we have to make use of even and odd functions. This one here is odd. This one here is even. If you multiply an even by an odd, you get an odd. And if you integrate an odd function on a symmetric interval about 0, you get 0 again. So all of those are going to give you 0. Okay? On the other hand, if you find your b sub k, that's going to be 1 over pi times, here's your function, negative pi to pi of x sine of kx. Okay, and I just thought I should have done this. I should have doubled it from zero to pi. It would have been easier. But I'll follow my notes here. But this is odd. This is odd. If you multiply two odds, you get an even. And for an even, I could just make this from 0 to pi and double it. Okay. In fact, shoot. Let's trying to think what it'll look like. It probably won't make a whole lot of difference. I'll just follow my notes. Okay, so you're going to get that. Here you have to use integration by parts. So this is going to be your u. This right here is going to be your dv. And so that's going to end up given 1 over pi times uv is going to be negative x cosine of kx all over k from negative pi to pi, and then plus the integral from negative pi to pi of cosine of kx over k dx. And this thing right here goes to 0 again because of the symmetry of the trig function about the origin. So this whole thing is going to be 0. So all we have to do is stick in the values of pi right there. And if you do, I'm just going to put in pi there, and you put in negative pi, and by the time you're done, you got to be careful. You're going to get well, it's not so hard actually. Negative pi times the cosine of kx all divided by k, subtract another pi cosine of kx all over k, and those pi's go away with this one, and I end up with negative 2 over k times the cosine of kx, which you need to to think about what that's going to be for even and odd k's. If k is even, that's going to be negative 2 over k if k is even, and it's going to be 2 over k if k is odd. Okay, and so now I'm going to have to erase this. Sorry, lack of space here as always. But now if you actually use the formula and stick these in as your a sub k's, these are your a sub k's now, or your b sub k's actually, b sub k's. They're the things in front of the sign. You're going to end up with here it is. Here's your f of x. And so here's your, I'll just use a little tilde to mean that this is the Fourier series that converges to it. It's going to be 2 over 1 times sine of x, and then minus 2 over 2 times sine of 2x, and then minus, it should be, let's see, when k is odd, so odd it should be back to plus again, so it should be plus 2 over 3 sine of 3x minus 2 over 4 times sine of 4x, okay, and then plus 2 over 5 for sine of 5x, and so on. And if you go to Decimus and graph that out, it'll really be cool what you get. You're going to get something that looks like this. Here's your graph, and then it just repeats doing the same thing again, and you're going to get something that just kind of, and it goes down here, and it just kind of crawls up that thing, and it's just really, really cool the way that works. Okay? Let me do one other one for you. This is a really cool one. One of the most interesting one is what happens if you have just a square wave. Okay, just a square wave. Okay, so in this case, here's what we've got. We've got a function that just is 1 there, and it's negative 1 there. Okay, so there's pi, there's negative pi. And I'll just give you some of the details here. First of all, you check out that a naught is going to be 0, because this is an odd function again. And a sub k is also going to always be 0, because this function, notice, is odd. So this is the function f. So if you integrate f of x times the cosine of anything, this is going to be even. This one's odd. So this is odd. This one's even. That's going to give you 0 by the time you're done. So that one goes away. Finally, your bk. Your bk, here's what we have. 1 over pi, negative pi to pi of f of x times the sine of kx. Okay, now notice, this one is odd, this one is odd. If you multiply two odd functions together, you get an even function. And for an even function, I can just double this and go from 0 right there. Okay, so you're there. And now that I've done that, I can just put in what this function is from 0 to pi. From 0 to pi, it's just 1. Okay, it's just going to be 1 is all. Okay, so that ends up just being 1. And by the time you integrate that, I'll just go ahead and give it to you. You can work out the details. But b sub k, it's just the antiderivative of that. And you're going to get 4 over pi 4 over pi times 1 over k, I should say, when k is odd, and you're going to get 0 when k is even. Okay, so you put those in as your bk's in this original thing again. And all your AKs are 0, and you just multiply each of these BKs times the sine of kx, and here's what you get. you're going to end up with, here's your function, f of x is 4 over pi. Let's just multiply that out front. Each one has a 4 over pi. And then it's just very simple. It's just the sine of x over 1 plus the sine of 3x over 3. Just all the odd ones. Sine of 5x over 5, dot, dot, dot. And again, you go to Decimus and go out a ways with this thing. And you're going to see that it's just really kind of cool. Here's your original function. And you're going to get this thing that kind of wraps around there and then wraps around there. A lot of cool stuff. And this is used by musicians, things like this. If you want to, if you have some sort of a periodic function like a musical concert or anything in music, that's all periodic stuff. Then basically you can get as close to that as you want to by taking a Fourier series. And once you have the Fourier series, all you have to do is just keep track of what these constants are in front. And by having those constants in front, you basically have all the information you need for that whole wave. For that whole wave, you've got that whole wave just by knowing what these constants are. And so Fourier series is a way that you analyze lots and lots of things that are periodic. Okay, so engineers use this a lot. So pretty rough, okay, but this gives you just an introduction to, as I say, a whole new area of mathematics that's fascinating, okay, fascinating area. So it's just another way that you can converge to functions other than the Taylor series. This one's called the Fourier series. More than likely, if you haven't heard of it before, if you stick around mathematics and the world of STEM much, you'll hear it. Very good. Thank you much.